Hi folks, today we are going to speak about how to leverage Apache Ignite SQL. Mostly we will focus on the distributed SQL pitfalls. We are going to improve our understanding of how to avoid common mistakes, even how to find out if you faced them already. So let's start. Let me introduce myself, a couple of words. My name is Vladimir. I work at GridGain Systems. Uh, I work as a part of customer solution team. We are responsible for the communication between GridGain and GridGain's customers. Also, I contribute to Apache Ignite project. So let's move on. This talk consists of several parts. First of all, I'm going to present Ignite SQL Engine overview, its capabilities and features. I'll do my best to make it quick. As the second part, I'll reference some typical pitfalls that users can face. After that, we are going to discover tools that aim to troubleshoot cases when queries work in a kind of unexpected manner. We'll have a look at a couple of typical usage scenarios after that, and eventually we'll establish maybe something like a checklist for SQL queries. So let's start with the overview. Well, first of all, here are the links to some talks related to Ignite SQL. How to start using Ignite SQL by Ivan Rakov, Apache Ignite Troubleshooting by Stan Lukyanov, and Getting Started with Apache Ignite SQL by Igor Silverstov. Well, they are really useful, then take a look when you have some time for that. Well, they're good. So, Ignite SQL supports syntax of the SQL 99. It means that you can use regular SQL queries, but it doesn't mean that all SQL 99 features are currently supported. So distributed joins, aggregations, and sorting are supported. So we can change data schema on fly. It's possible to alter tables, to create or drop indexes. Ignite SQL transparently works with both in-memory and disk data. Now, I'd like to say a few words about how queries are actually executed across Apache Ignite cluster. There are no dedicated nodes for that. SQL Engine resides on every node. Actual queries are being executed as close to your data as possible. Cluster does its best to achieve that, at least. Let's have a closer look at the subsystem responsible for execution within a node. Its main part is query engine itself. We often say that H2 engine is utilized for that, but to be honest, it's not 100% true. Our engine is based on it. For example, in GridGain Community Edition, it has been already forked, even forked. The engine is plugged to index structures created for SQL. Index structures, in turn, reference key value partition store. In general, it's pretty fair to say that the engine uses index structures only, but sometimes it could fall into the partition key value store if indexes are currently being rebuilt and therefore unavailable, or maybe for some other reason. But now I'd like to say, well, about like more about MapReduce concept, because it's being used for distributed queries. Every query consists of two main parts, map and reduce. Map queries will be executed on every node that stores data for a query. Reduce phase will be executed on the node where the query was initiated. For a thin client, it would be a node serving a connection with the client. A process dedicated to dividing a query into those pieces map and reduce, is called split, and the module responsible for that is called splitter. Uh, let's have a closer look at the engine. It consists of two major parts: H2 engine or H2 based engine, and Ignite SQL engine itself. H2 is responsible for local per node execution. Ignite SQL for query orchestration. In fact, there should be an arrow from every Ignite component to, well, to the H2, as it's used on every step more or less. Like the only actual exception is simple parser. Well, it's being used to parse Ignite specific commands. Well, for example, splitter first of all calls H2 to get a plan for a query. What's really important here is that all the data is stored in Ignite and wrapped by H2 iterators. So H2 only duplicates some schema information in order to make parser, validator, and planner work. Now I'd like to discuss affinity. We'll definitely need it later. It's required if a table is partitioned. We have a key, but we use some function of the key to spread data across a cluster. In this example, cities from the same country have the same color. You can notice that data is being kind of shuffled in terms of country. It's not good or bad, it's just how it works. Let's imagine a situation where we would want to manipulate this layout. To achieve that, let's define an affinity column for that. So affinity key is country ID for this city table. So as you can see, like all French cities reside like on the first node. Well, there are several useful flags. Classic DB users could treat them as hints, well, because it works kind of that way. Lazy equals false means that data is being accumulated in memory. User starts receiving data only when a query is finished. So with lazy set as true, the engine does its best to process and transfer result sets like in some iterative manner. Enforced join order stands for, well, it prevents query optimizer from changing an order of joins. Sometimes you can know better, but not always, but sometimes. Distributed joins, by default, there is an assumption that everything is collocated, like something like we discussed on the previous slide, and it's okay to join locally between tables. So if you'd like to have like different behavior, you should specify it as true if you want like to join in distributed manner. But keep in mind that distributed joins works with equi-join only, and indexes should be present on fields used for joining. Collocated flag. Well, I always say that it should be called collocated group by. In general, it means that all data for aggregation is available locally, and it should be done locally. Skip reducer on update works for updates. Allows to make in-place mutations calls on a mapper. So, well, it could be useful in some cases. We'll need some of them later, so let's move on. Let's have a closer look at the current SQL engine capabilities. Well, what the engine can do. Index pickup could be optimized, and sometimes the engine is able to take care of a join order. There is a static optimization reorganizing subquery to join when it's possible to do that. It's pretty fresh. It was implemented recently. Also, it's worth mentioning that there is a machinery responsible for memory tracking and offloading, but unfortunately this feature doesn't exist in Apache Ignite. It exists only in GridGain Community Edition because it requires forked H2. So I'm not aware about plans to introduce it like in Apache Ignite. So right now it's GG's Community Edition only. Um, well, the main current MapReduce drawback is that only one MapReduce phase is possible. It means that we can't calculate and aggregate in distributed manner and then transfer it to another query as a clause. So, well, because of that and because of many other reasons, there is an initiative to re-implement the engine. It's being developed at the moment. It's going to use Apache Concise under the hood. I'll leave a link to the proposal. Well, it definitely worth mentioning because it will change a lot of things and the improvement. Yeah, here is the link. Well, let's talk a little bit about diagnostic tools. So, what do we have here? Well, basically, query plan is a very powerful tool. It's it's used to understand how planner worked, how optimizer worked. System views are also good for troubleshooting because they store some information about static data and about query state. So metrics metrics are useful as well because it's focused. Well, metrics are focused on cluster state and engine state itself. Also, tracing and logs are available. Well, I'll focus on all of them in the further slides. So the aim of I'll give an example of a query plan. The aim of this example is to explain how to read Ignite execution plans. To get a plan, first of all, to get a plan, you just need to add the explain prefix to a query. You'll get a result set. With multiple rows. Each row describes one query stage. For this particular query, it would be just 2 rows. Well, first one and second one. Well, the last one is always the reduce part. So it's the second one in this case. It looks pretty good. I mean, the query looks pretty good because it leverages index on the mapper side. It's IDX0. It's on the reducer side, it looks really minimalistic. Merge scan, the most important thing here is merge scan on the reducer side. It means that this reducer is really trivial and effective. It will only fetch and merge partial results from mappers. Let's dive into a plan for a query which is a little bit more complex. We'll need a corresponding schema for that. We remember city from the first example, and there is a country. So country ID is like a reference to the country. We are going to get a name and population of countries that have average city population above some predefined argument. So here is the query. This one is meant to reproduce a case when where intermediate results are being passed to another part of a query. In our case, it's a distributed join. Look, it's inside. So, well, what we can see, it's, well, we have two map queries here. Well, so Query Splitter decided to split the original query into two queries. These two queries are being executed independently during the map phase. The reduce phase uses both results. The first one projects into a virtual table 1. Second one projects to a virtual table 2. Let's keep that in mind. We'll need that. What information can we extract from the plans? We can see indexes proposed to be used by the engine. In this particular case, we can see that the aggregation is really effective because of a sort-based aggregation instead of like hash-based on. Well, group sorted tells us about that fact. Just well, okay, guys. Let's recall what we discussed on the previous slide about virtual tables. T0 is a result of the first request, so T0. And T1 is a result of the second request. The plan is pretty big, but it's possible to understand an actual join order here. So we can see, well, second is second, first is first. It would be really great to have a closer look at the second T1 part. Well, this one. So let's recall how the corresponding map part looked like. It seems that the entire country table is being fetched here. There is no filtration on the mapper side, but it's okay. It's okay for this particular case because the reason is the size of the country table. It's fortunate that there are only about 200 countries in the world, so it's okay to fetch like everything. But keep in mind that if your table is big, then this pattern will trigger extensive memory and network pressure, as a reducer will need to hold a copy of data collected cluster-wide. So the moral here is know your data. Well, so let's sum up. What useful things could be extracted from a query plan? It's join order, index usage, and splitter result. How it was actually split. Well, another useful tool is system views. System views are documented, so I recommend to have a look just in case you feel interested. Well, here is the link. There are like two major group of views. In general, it's quite easy to forget names of views. So there is a meta view in the sys schema to remind about the list of available views. Well, about two groups of views. First one is views about data structure. Second group is about cluster state. So it's about what's happening. It's about how it looks like. What useful stuff can we extract about our data structure? We can get information about table layout, for example, including affinity and types. So it's very important. Well, I'll give you more details about this topic later, especially about indexes and inline size in particular. Well, one can request information about queries being executed on a node with help of this one special view. It's SQL queries, but currently it's entirely local, so it's per node. Well, metrics are documented as well. Well, have a look at the link. Well, there are several built-in exporters for metrics. JMX is a classic like Java style exporter. You can use it, you can leverage that. SQL View, like metrics are being stored in sys metrics like view, so you can use that. Well, you can use OpenCensus. It's possible to export metrics to a tracing span, and logs are our good friend. So it's possible to periodically dump metrics to your logs. So, well, what metrics are useful? Well, index.io, it's a real usage of your like it's about data transfer. It could be useful to validate your load profile. If you have some expected load profile, you could compare it to actual observation from this one. So prepared query is about hits and misses on the cache of execution plans. And finally, third one is about alerting metrics. It works strictly in GridGain Community Edition because of the H2 fork. Well, free mem, it's about memory. Well, how much memory left? Basically, that's it. And a floated queries number is about how many queries were actually offloaded to disk. So, and if offloading was used at all. So tracing feature is still experimental in Apache Ignite, and but anyway, it's documented. You can have a look at that. Well, it's compatible with OpenCensus protocol, and it means that you can export them, for example, to Zipkin. Well, this snippet shows that it's very simple. For example, if you have a Zipkin instance like running locally, you can export there. Well, let's have a small demo. Well, in this demo, we established JDBC connection to a cluster. After that, it becomes possible to see a query that is stuck. So it's being executed for, it had been executed for about 30 seconds. Please keep in mind that query unresponsiveness was emulated intentionally for the purpose of this demonstration. So a query must be fully finished in order to be transferred to the tracing subsystem. Currently, it's not a real-time connection between SQL and tracing, but it doesn't look like a big limitation as queries are being repeated pretty often. So this feature doesn't seem to be of great demand at the moment. So why I said that? Because we need to kill the query. So yeah, it has been done. So now it's not running. So let's remember the ID from the console. It's okay. It's 10103. So we are looking for the query using its ID recorded from the console. Well, yeah. So we need to look by tag. We need to search by tag. So after that, we can start investigating. So first of all, we need to figure out if it's correct query. Like, so there is a text, like there is a text of the query, so and ID of the query. So it is like the query that we are looking for. So, well, what we can see partitioned reservations here. It's useful because, well, it can help us to understand whether a query reserves correct partitions or not. Maybe it's unexpected. Well, so let's have a look at actual like page requests. So node 1 responds fast, but node 2 is slow for some reason. So, well, that's a red flag. So something bad is happening on the second node. Well, yeah, here we go. And also it's possible to see how many records were actually fetched. Well, and when a map query is finished, we'll see a text representation like some representation, including a plan and the scan count. We'll see it many times today, but a little bit later. So, okay, let's move on. Okay, so the logs. It's useful for like, well, you can see errors and exceptions there on map nodes. It's useful to see exception on map nodes, especially for thin clients, because they don't always get full error messages. Well, they often get truncated messages. Well, but like the most like important and useful thing here is is warnings. Warnings. There are three main types of warnings. It's long-running queries, queries with huge result sets, and inline size warnings. By the way, it's somehow configurable. For example, long-running and huge results warning can be tuned. Multiplier is a time frame to repeat messages, and well, threshold and timeout is like they are threshold values to trigger the alert, to trigger a warning. Well, so it's an example message of a long-running query. We can see duration here. It's 2 seconds. It's about 2 seconds. We can see type. It's map query. Well, it's only possible to see state of a query only if it's a map query. Also, it's possible to observe flags, well, that are being used by the query, and well, execution plan eventually, and the state. So it's like how many records were scanned and how many lookups were made. So huge results example, it's pretty similar to the previous one. It's a good practice to keep your result sets as small as possible. For example, here it's pretty big, to be honest. Well, so I don't think that it's good, but it all like depends on your actual use case. Maybe you are prepared for that. So, and yeah, scan count and lookup count again. Well, inline size. This message says that we should increase index inline size. We can see like table name and index name but we'll focus on the inlining separately a little bit later. Well, I mean, these tools are all separate, but we have GridGain Control Center. It unites them somehow. So what we can do here, there are a lot of like different functionality. We can configure metrics. We can set up alerting based on our metrics, and we can access SQL. That's like the most interesting part in terms of this presentation. We have separate tabs for important views, well, like running queries and query statistics. Keep in mind that GridGain Control Center has them aggregated, not per node, so it's already aggregated. Well, it's a major improvement if you compare it to the native SQL view. So we can execute queries here, etc. And we can so there is a tracing window. We can see the same picture as in Zipkin. We can inspect spans, etc. So it looks like really pretty. Well, that's my opinion. Thanks. Okay. Well, let's focus on the analysis. So, for example, well, it's about how to troubleshoot your issues. This one works okay for a cluster with a single node, but breaks for multi-noded installation. Experienced Ignite users might have already understood that it's all about collocation. Join happens by country ID, right? Let's query a system view and understand actual affinity layout. Something like that. Yeah, here we go. Okay, what can we see here? Country ID is not the affinity column for the city table. Let's keep this fact in mind. Here is another example triggering wrong query results. This one fails even on a single node cluster. The root cause here is an optimization allowing to go directly to the right partition in case there is a corresponding clause. Maybe you already guessed that, well, what's the actual reason? So yeah, here it is. Um, well, you can you can visit the link. Well, it describes like this optimization. But let's move on. Well, now we are ready to figure out how to fix that. There are two options. First one is to establish a correct affinity key. In that case, it's country ID. So it will make a city live in the same partition as its country. So it will like repair the case. So second solution is to make the table replicated. It could work in case you have enough capacity for that. Well, because it means that the underlying cache will be stored everywhere, but it will still repair the case. Well, you should be cautious when you're using SQL and Cache API combined, because Ignite APIs have interoperability. It's a very powerful tool, but with great power comes great responsibility. So it's pretty straightforward to get sizes diverged here. For example, well, by sizes, I mean select count one from test and cache size. Well, index structure here observes only ID 0 and ID 1, but well, nothing prevents you from inserting like a record with additional field, which won't be observed by like SQL machinery, but it will be observed by Cache API. So like be cautious when you maybe you use that for validating or etc. It could cause some difficulties. So Ignite. Oh, now about like inline size. Finally, uh, Ignite SQL engine can calculate it automatically, taking some internal information and considerations into account. In general, well, there is no good solution for that. It's always a compromise. So because like big structure, well, it's slow to traverse big structures. So it's always like something between. Well, let's discuss actual structure of like of inlining. So in the inline row, for each value, 1 byte is dedicated to a tag that stores type information. Well, for integer is like it's 4 plus 1, it's 5. For a long, it's like it's 8 plus 1, it's 9. Well, it becomes more interesting with with a string because there is an additional size like size chunk, so it stores actual size of the string, and well, string itself is being trimmed, and well, in most cases that's the reason of like inefficient usage, because it trimmed in case it's like it's more than the dedicated space, and it's filled with zeros in case it's less than the dedicated space. And binary object is being stored as well as a hash. In most of the cases, it's enough to maintain effective tree structure. So to ensure that records are truly unique, primary key columns will be added to every record. Ignite doesn't store row ID because it's extremely complicated to maintain such structure in a distributed solution. Well, how does it physically work? Index structures like should store records of a fixed size in order to be performant. Mm, so when you traverse an index, and inside of it you traverse a row, on every value you can like get kind of 3 results of a comparison. So it's less, more, or I don't know. I don't know means that, well, value is not like enough to understand whether it's bigger or lesser than like than the argument. So it triggers like our alert, our warning. So uh, at this point, nothing super intelligent happens. The engine will recommend the length of the affected line, so the entire length. Well, it could be not. It could be not like a, not a correct like suggestion, but like the engine tries its best. Well, I'd prefer. I'll come up with like with a couple of advices. So first of all, uh, the most selective column should come first. Well, because maybe it would be just enough, well, to truncate everything else. If we need an index containing a string with constant prefixes, then we definitely need to add prefix length to inline size. Otherwise, you can get into double trouble. You'll neither have a small cozy index nor any speed up improvement. The index will be totally polluted with constant values. So I'll give an example. If you need to store, for example, file path information, you'll surely face the issue because, well, uh, it's a constant prefix. Well, it's a definitely like a constant prefix. It will grab like the entire index for that. And in this case, if your inline size is less than 17, it will be like totally unuseful, and it will be just a waste of like of memory because, well, our we have like 14 constant characters, or, well, kind of. So another example is like, imagine that you have like first part of an index as batch ID. It's Unfortunately, it has only few unique values, so it's not like very selective. So, and in this case, we need like to, well, and the second part is it's like UUID. It's a fixed size type. So, and it's like very selective. But, well, in this case, it will be a waste of memory in case of inline size is less than 23, because we need to inline like these, like, well, these strings, because they're sort of unique. And don't forget to add inline size of your primary key. So, well, let's discuss some like high memory consumption issues. For example, here we can see that, well, we query a view like of history. Uh, well, assuming that like memory max is big. So, for example, we get one query. It's, well, we select like star from test, where like type is 0, ordering it by name. So why it consumes a lot of memory and kind of slow? Because in the execution plan, we can see that it utilizes IDX type to, to filter by type, but it makes sorting. So, well, sorting stuff is being grabbed, to heap, and, and sorting is slow. So what we can do here? For example, we can use a hint. For example, if we use like IDX name, we can leverage that it's already sorted by name. So, well, the magic line here is index sorted. It means that it just grabs from like one by one from the index, and it's like applying a filter after that. But and it's also possible to make it lazy in this case. So let's speak a little more about lazy. So if your lazy is set as false, it's like accumulates results, well, in the heap, because, well, it doesn't give like anything to user before it's like accumulated, aggregated, etc. So, well, but if you have lazy set as true, well, it works more like iterator. Well, so that's not always possible to do that, but sometimes it's really possible. It could become tricky with sorting, as we noticed on the previous slide, and with aggregation. So it's not a silver bullet to return memory usage, because it's like not always works and not always work. And performance impact for small result set is like you can sense that, but it's applied only for like tiny result sets, like 1, 2, 3, maybe 10 results, because there are additional costs for tables to lock them. Well, and it's not implemented for reduce phase. So on the reducer side, if you have some like not trivial complicated reducer, you won't be able to do anything like in a lazy manner. Well, so let's discuss like what we can configure about that. So in fact, those SQL configs could be different for some nodes of a cluster. It works that way because it's possible that they have different hardware at least. Uh, so, well, let's focus on those three. Global memory quota, well, is responsible for like, well, its name is kind of speaking. It's global memory quota. It's like a sum of quotas. But like as far as I remember, it's about 60% of heap. Yeah, and well, offloading enable like it enables spilling to the disk. You should like definitely pay attention to that because it works pretty good with sorting, but in some cases it's possible that it it won't perform so good for grouping, for example, because of the nature of those operations. And finally, SQL query memory quota is for one particular query, and it's turned off by default. So, well, let's form a checklist. So data collocation is good. Well, like it's really good because in distributed systems, it's advised to do as many heavy lifting locally as possible, and collocation surely helps with that. Lazy execution mode is our best friend because we won't give additional pressure to our heap, and like we will traverse our result in a more iterative, reactive manner. So don't forget about indexes and plans and hints. Well, they will help you with that. So and don't be sometimes it's okay to not be shy and to say use index, because sometimes like um an engineer knows better than the engine. So join order is a very crucial, because it's the same like the previous one. Sometimes the optimizer cannot figure it out to make it right, and you need to experiment with that, because some orders work definitely better, surely. Well, it's more a matter, I mean, for me it's more about making some attempts, changing and checking the results. Well, index inlining and index structure. So to avoid additional page lookups, I mean, to avoid going to the value and just staying inside of an index, it's really useful to have your inline size tuned correctly. And of course, index structures, selective fields first, don't forget about that. And as I mentioned before, the only simple static optimization is rewriting subquery into join that was actually implemented. So don't hesitate to make it yourself, because some simple stuff like index usage with OR So it's possible to rewrite or to union all, and it's okay. Like, it's pretty straightforward. So, well, there is a couple of useful links. So it would be great if you like visit them if you have like some time, because well, it's useful information. So thanks for your attention, and well, now I would be glad to answer your questions if you have any.
Does inserting data take more time in cluster as compared to a single node?
Well, it surely like depends on how you do that. So for example, if you do it like in a parallel manner, so it's distributed correctly, so it should be like faster, definitely faster, because well, each node maintains its own like index structures, so you are kind of spread your load across your cluster.
And then maybe one last question. Is it possible to get heap metrics for each cluster node individually?
Well, technically they are individual. So for example, GridGain Control Center aggregates them, or you aggregate them like as you wish. But for example, JMX shows like local metrics.
Okay, great. I think that's all the questions we have right now. And as I said, we'll be sending a link to the recording after the webinar. Thanks, everyone.